Thank you, John, and thank you, Julie. And thank you everyone who have made the Equinox Summit possible, including all of you who have come here today. Ladies and gentlemen, we face enormous challenges in the decades ahead, but we are also at the peak of our prowess and well-being as a species, since first venturing from the savannas of Africa 100,000 years ago. Never before have so many humans lived so well and for so long. We vanquish deadly diseases, travel enormous distances at will, build great structures and exploit massive energies to power our civilization. We have mastery of our planet like never before in human history. But this remarkable success also has its costs. And it's to address these costs and how we might harness our extraordinary capacity for scientific and technological innovation to meet them that we have gathered here at the Equinox Summit. Over the next hour, we're going to introduce you to some of the themes of the summit. We'll start by showing 4 short benchmark videos which summarize the issues, and they are the trouble with carbon, how we generate electricity, how we distribute electricity, and how we store it. Each video will outline today's state of affairs and give us a taste of what's to come over the next 20 years or more. Following each video, we will speak with some of our summit participants. So let me introduce you to our distinguished guests. Barry Brook is a climate scientist who holds the Sir Hubert Wilkins Chair of Climate Change at the University of Adelaide and is a director of the Environment Institute. He and I will discuss the trouble with carbon. Walt Patterson is Associate Fellow in Energy, Environment and Development at the Royal Institute of International Affairs, known as Chatham House, and a visiting Fellow of Science Policy Research at the Science Policy Research Unit at the University of Sussex. We'll discuss energy generation. Jatin Nathwani holds the Ontario Research Chair in Public Policy and Sustainable Energy Management at the University of Waterloo and is a director of the Waterloo Institute for Sustainable Energy. We'll be discussing electricity distribution. Robin Batterham is the president of the Australian Academy of Technological Sciences and Engineering, a former chief scientist of Australia, and a former chief scientist of the global mining giant Rio Tinto. We'll discuss the promise of energy storage. Welcome to all. But to begin, let's watch our first benchmark video on the state of the planet and why so many scientists are so worried. It examines, in a nutshell, the issues with carbon, past, present, and future. So let's take a look.
It's everywhere. You see it on the news, in your newspaper, on the net. We're running out of oil. The use of coal and oil is at its highest peak in history. Energy prices are going through the stratosphere. We are dependent on non-renewable fossil fuels, what some call high-carbon energy. And at the rate and way we're using energy, that might lead to irreversible damage. A global crisis is coming. What will we do? Will factories go silent? Homes dark? Economies grind to a halt? The world in chaos? Terra incognita? Or is there a map we can follow? Life on Earth has always emitted carbon dioxide, also known as CO2. We all exhale CO2. It's a natural component of the atmosphere, used by plants in photosynthesis to grow and thrive. Photosynthesis is driven by the sun, and the sun's light inspired us to create and control our own illumination, eventually creating the electric light bulb, which we powered by burning coal. We transformed our world with all those bulbs, and the other electrical devices that followed. In addition to coal, we burned other fossil fuels, like oil and natural gas, which produced a lot more CO2 than our planet can use and greatly increased our carbon footprint on the globe. CO2 in the atmosphere is measured in parts per million. But what does that mean when we can't actually see it? Imagine the carbon dioxide gas as a solid. Think of soot. Each year, we're emitting 8 billion metric tons of carbon dioxide. If that were soot, we could fill up about 1 million rail cars. Since the Industrial Revolution, we could have filled 430 million rail cars, enough to circle the Earth 190 times. Today, the CO2 in the atmosphere is like a thick blanket around the Earth. And as the blanket grows heavier, the planet gets sicker. The symptoms are always in the news: violent storms, floods, droughts and fires, melting ice caps and glaciers. 350 parts per million is the accepted carbon blanket in the atmosphere that would keep the planet livable for the human race. Prior to the Industrial Revolution, we were at 289 parts per million. By 2011, it grew to around 392 parts per million. In 2030, some predict we will exceed 450 parts per million. Experts say we face catastrophic losses for every living thing on Earth because our reliance on high carbon energy is jeopardizing our future. Plus, our population is set to grow to 9 billion by the year 2050. There are already 7 billion people on the planet today, and 1.5 billion of them don't have access to modern electricity, but want it. So, if we're to satisfy present and future energy demands, and ensure our ability to thrive on planet Earth, we must examine cleaner and more efficient ways for the generation, distribution, and storage of electricity.
Well, Barry, that's a lot of numbers and timelines there. Is 450 parts per million really something to be worried about?
Well, yes, it is, because if we look back over hundreds of thousands of years, then we've never had that concentration of CO2 in the atmosphere. And if we've reached 450 parts per million by 2030, it means we've been continuing to emit large amounts of carbon and continue to be heavily dependent on fossil fuels for the next 20 years. And if that's the case, it's going to be very difficult not to get to 550 and 650 and 750. And as you increase that concentration further and further, it's like a drunk who continues to consume alcohol. You know,
so it's a little bit like a roller coaster ride, is it?
And then the other problem is that the Earth starts to respond more and more vigorously, and these feedbacks start to be imposed on the Earth system, and that can release carbon dioxide that would otherwise be locked up. And so the Earth itself can start to be a source of carbon dioxide. We really don't want to go there.
But it's not like carbon dioxide is evil. We actually need it for life on Earth to exist. The Earth would be too cold without it. Isn't that right?
That's right. And a good way to think about that is the Moon. It's in the same place in space. It has no atmosphere, so there's no greenhouse effect. And during the day, it's hotter than anywhere on Earth. During the night, it's colder than anywhere on the planet, including Antarctica. Its average temperature is about 33 degrees lower than the Earth, but it fluctuates wildly. We need the greenhouse effect to keep a modest and livable climate. But if we start to push that climate system towards a new equilibrium, then the whole Earth is going to have to adapt. And if we do it very quickly, that adaptation is going to be extremely challenging.
So is the problem then the extra 8 billion tonnes that we're pumping into the atmosphere?
Yeah, and 8 billion tonnes sounds like a lot, but in fact, the natural carbon cycle transfers perhaps 100 times more carbon through the oceans and atmosphere each year. However, if you can imagine a bathtub and you take a bucket and scoop the bucket out of the bathtub and pour it back in, you're not doing anything to change the level. Whereas if you start to get a hose and put it in the bathtub, even if it's only dripping, the bathtub starts to rise. So there are these huge transfers of carbon going on naturally. We're adding extra to that, and the planet can't absorb that rapidly enough because that carbon is fossil carbon that's been locked up millions of years ago.
Clearly, reducing our emissions is what's needed, but it's not a simple process, is it?
No, well, if it was simple, then countries that weren't naturally well endowed with fossil fuels would have already made that transition to lower carbon energy sources. The fact that instead they've relied on importations of oil and coal and gas means that it's very challenging to move away from a predominantly fossil fuel-based economy to something different. Will be difficult. We can look at some countries in the past that have achieved that in some sectors, such as France for nuclear and other countries for hydroelectricity. They are particular circumstances that are worth considering how they've done that, but globally we're a long way short of transforming these energy systems.
Okay, well, then is the way forward to develop new and transformative technological solutions if civilization is not only to survive but thrive?
Yeah, I think new and transformative energy systems will be really important, but I think we also need to recognise that we've invented a lot of fantastic energy systems over the last 50 or more years, and we haven't deployed them at anywhere near the scale that is required. So yes, we do need to keep on inventing and thinking and inspiring new ideas, but at the same time we need to work really hard at looking at the best technologies that exist now, getting them commercialised, getting them more cost effective, and really starting that rapid movement away from fossil fuels.
Well, that's what we're trying to do here at Equinox Summit. We're going to reboot the dialogue. Well, that's our problem in a nutshell. Our growing demand for electricity and the need to find cleaner ways of getting it. At this summit, we'll be attacking the problem from three technological angles: generation, distribution, and storage. So let's watch the next benchmark video and take a look at our first piece of the puzzle, generation. We'll see how much electricity we consume today and how much more we may need in 20 years. Let's take a look.
When the first urban power plant was installed by Thomas Edison in New York City in 1882, it served only a small neighborhood and burned a modest amount of fuel. One plant, 58 houses. But as power stations and a delivery grid became a universal concept, the globe's energy requirements became colossal. We began with coal as fuel, moved on to oil, and added natural gas to the mix, all of which have contributed to our problem with CO2. Somewhat cleaner sources of energy were tapped throughout the 20th century, with hydroelectric stations and nuclear plants. And while there is a movement toward clean energy generation from solar and wind, these sources are rolling out too slowly to close the gap between the world's energy supply and the growing demand. As it stands, almost all power generation in the next 20 years or more is going to involve fossil fuels, with coal having a massive resurgence. The world is currently struggling to generate 22 trillion kilowatt hours of electricity per year. Most of it is coming from high-carbon fossil fuels. And by the year 2030, experts predict we will require another 40%. That's 30.8 trillion kilowatt hours per year to power the planet and meet demand. Most of that increase involves rising energy needs in the developing world. Clearly, we need to bridge that gap, and not by relying on high-carbon, non-renewable sources of energy. Creating efficient, clean, and sustainable forms of power production is critical. Is a scientific or transformational technological answer to this crucial global problem within our reach?
Walt Patterson, we're struggling today to generate 22 trillion kilowatt hours of electricity annually, mostly from high-carbon sources. By 2030, we're likely to need 31 trillion kilowatt hours a year. How in the world are we going to meet this demand and reduce our reliance on fossil fuels?
I always think that if a problem looks insoluble and you know you have to solve it, you'd better be sure you're describing the problem correctly. I think the problem we have here starts with the fact that we have an electricity system that's based on a technical model that's more than 100 years old. It's based on criteria that applied at the turn of the 19th century. not the turn of the end of the 20th century. What the technologies that were available at that time are overwhelmed by the technologies that we now know are available. If we were starting from scratch now to design a planetary system to deliver and use electricity the way we want to, it would look absolutely different from the electricity systems that we have. But we have replicated this century-old system all over the planet. And not only the technology, but also the institutions and the finances, and most particularly the mindset about electricity in society. And that, I think, is where we really have to start addressing the problem. Are we doing this right? Is there a better way to do this? I am convinced there is.
That's why we need new thinking, isn't it? Tell us, what is baseload and why is it such an important consideration?
If you work on the basis that you have a mixture of generating technologies that we have these days, some are very inflexible and cannot be started up and shut down very easily. And so they are run continuously, but of course we don't use electricity like that. We use electricity very, very flexibly. We turn things on and off. We use a lot of electricity in the evening when we have lights on. We use a lot of electricity in the daytime when their office is working. We use comparatively little electricity in the middle of the night, although there are industries that are working through the night. So the amount of electricity that we're using, even over a 24-hour period, varies up and down, sometimes by as much as a factor of 5. And these big stations can't cope with that. You have to have a lot of smaller stations or stations that are more responsive. The big stations are what are called baseload stations, and this goes back to the time of Edison, when the only technologies available were water power and steam power, and they had huge economies of scale associated with them. So in those days, a better station was always a bigger station, usually farther away. That no longer applies. We now have the opportunity of actually making very good stations that are small and close to where you want to use the electricity. And that's going to be a very important criterion.
So we need efficient, clean and sustainable forms of power. That's critical, but there's no magic bullet.
There is no single magic bullet, not at all. That is actually one of the things that we have to get used to, is that there are a lot of different applications of electricity. Some are very sensitive, some are very demanding, some are not sensitive or demanding at all. We use an awful lot of electricity very, very wastefully. We use a lot of electricity which is high quality energy. We use it for moving the temperature up and down of maybe a few tens of degrees at most. This is thermodynamically very, very easy. Why are we using this high quality energy to do something which is actually much easier? If we got the buildings right in the first place, we probably wouldn't need the electricity to do that. So you have to start thinking in whole system terms. And I don't just mean the electricity system, I mean the energy system, including the user technology in which the electricity is actually doing its stuff.
Okay, last two questions then. Are there transformational technologies out there that could address this, but also, won't cost the earth or have negative impacts?
I think there will be transformational technologies, and as Barry says, we already know a number of them which have yet to prove how good they can be. Part of this is inertia. Part of this is what has been called legacy systems, where you have an awful lot of plant and technology and an awful lot of industries and corporations that depend on that plant and technology and are doing very well out of it at the moment. But the legacy systems are a drag on the rest of us. And we have to figure out a way to deal with the legacy systems and take advantage of the new potential for the new innovative technologies which are there.
Barry, you have some comments to add.
Yeah, and I think a fundamental point will be, if we're going to displace fossil fuels, we need to get these technologies as cheap or cheaper, so that it actually makes economic sense to invest in them. Until it does, it's going to be an uphill battle to actually get governments and societies to adopt them on a large scale. And part of that may be a price on carbon, but a fundamental part, I think, will be large-scale deployment, proving our innovation to actually develop these technologies which often don't require much or any fuel to be cheaper than fossil fuels which do.
I agree completely. That is going to be crucial. And let us not, although we're proposing to focus on the science and technology this week, the science and technology by itself is going to be sterile unless we have the institutional and the financial mechanisms in society to take advantage of the science and technology.
We'll be tackling that in the closed sessions. Thank you, gentlemen. Now let's look at the next component of the puzzle. That's distribution. How we move electricity around is really complicated, as it turns out, and not as efficient as it could be. Let's have a look at the benchmark video 3.
Generating electricity is the first link in the electrical chain, but delivering it efficiently and using it effectively are both difficult. Most would agree that the incandescent light bulb was a brilliant idea. Simple, elegant, and, of course, illuminating. But this brilliant idea also has a dark side. If coal is the fuel burned in a power plant, fully 65% of the energy is lost right at the source. Another 3% is lost during transmission to your home. Of the energy that does reach the light bulb, almost all is wasted as heat. Less than 2% of the original energy from the coal is actually converted into light. To light just one 100-watt incandescent bulb around the clock for a year, you have to burn 1/3 of a ton of coal. Coal that has to be mined and shipped to the power station, requiring even more energy. By switching to a compact fluorescent bulb, we reduce the amount of energy required, but the bulb is still wasting 30% of the energy it draws as heat. No matter which light bulb we use, underlying inefficiencies in our system contribute massively to the CO2 problem, such as phantom power loss. Electronic equipment in our homes and offices that are on standby, like TVs, stereos, and computers, are using energy every minute of every day, collectively pulling a full 8% of available electricity out of the grid. We are wasting energy as heat, using energy we don't really need, dissipating energy through the grid, and losing energy at the source. Right now, the world is struggling to produce 22 trillion kilowatt hours of electricity each year to power almost every aspect of our lives. By 2030, we could save more than 50% of our CO2 emissions just by plugging the inefficiencies, energy that could be used to help satisfy the world's growing demand for power. What we need now are brilliant new ideas to shed more light on how to become more efficient and find much better ways to produce, deliver, and use electricity.
Jatin Nathwani, it sounds like the energy distribution system we have today could do with a lot more efficiency. What's your view?
Of course, the inefficiencies highlighted in the video refer to or reflect a fundamental feature of the physics and flow of power in the system when we go from centralized generation to high voltage transmission to distribution to service at your home. But the compelling message here really is around the question of inefficiencies and how we need to turn our minds and eye with a serious focus to being able to get at the question of not only inefficiencies but reducing cost in the system. That's one feature that's absolutely central here. But if I were to make an additional point on top of that, is really at the heart of this summit, how can we really bring to bear innovation, new technologies to this precise question of improving the efficiency of the system, reducing cost, in a way that it begins to get at the question of meeting the societal goals and going down the path to reduce a lower carbon footprint energy economy.
Let's tackle that. What do you think would be necessary to ensure a distribution system that could make a dramatic contribution to the reduction in emissions?
The 2 or 3 key features, of course, where you produce the energy and what is the mix of that energy are kind of two important parameters. So that takes you to a rethinking, if you wish, or perhaps an evolution of the system that moves away, partly at least, from a centralized form of generation to, let's call it, distributed forms of generation. To cut the jargon, really get at the question of now, how does the householder become, in fact, a generator? So you got your solar roof or geothermal. How do we get to a stage where, in fact, you begin to integrate other parts of the system, such as smart cars and chargers and other features? So you're really moving to a system that we call under the umbrella of the smart grid developments and ideas. So you're moving down a path that will enable to get you to a lower carbon footprint economy when it's a distributed sources of energy. That's one part of the puzzle. And then, of course, when you're at the distributed part of the generation, how you source that. So if you're going to use buckets of coal to do that, that isn't going to help. But if it begins to get into the question of newer, more effective sources of generation, such as solar, wind, and
so we had to break the problem down into its three components. But ultimately, it has to fit together, doesn't it? Yeah. Are there any transformative technologies out there that you think could give us these greater efficiencies?
Yeah, there isn't one such, but under what I would call the umbrella of really truly bringing a convergence of the information science and systems technologies and its marriage with the power system or the electricity system. That has, so this is others referred to as the digital economy or the digital transmission of energy and so on, that has the potential to really get at the question of both cost and efficiency, and in ways that we have not really thought our way through on that.
Walt, you have some thoughts?
Well, I was thinking that this whole system approach is really crucial. And now that we have the opportunity to incorporate so much information technology in the systems, you have, for example, the possibility of having an electricity system in which all your appliances talk to the generators directly, not through a dispatcher, not through a human at all. Just through the information technology that's incorporated in the network.
If I may just add to that point, you really are looking at a transition now that gets you to a level of a consumer, whether you're a homeowner or an industrial consumer, a level of control that you can have through real-time feedback and devices on your consumption, your ability to change your behavior in a way that is where you're going. So when we talked about information science and the convergence of IT, you really are looking at a very data-rich, information-rich system that allows people to do things. So just think of it, your smartphone or your BlackBerry, and being able to control what your fridge does or in your home. It's that kind of an idea.
You charge your smartphone from the smart grid. That sounds fantastic.
Anyway.
So it sounds like we've got legacy systems which we're trying to do what we need to do, but actually, if we can't really build them from scratch, Walt, which is what we'd all love to do, we have to try and find other solutions, yeah?
And there is a transition happening. We have to understand the limitations of our legacy systems, but as they age and the infrastructure is renewed, therein lies the opportunity now to do the transition, so not to build the same old things that we did, but begin to think in terms of the kind of ideas that are.
Okay, well now let's look at the last piece of the puzzle, our fourth and final video today, storage. Could the ability to store electricity, to bottle it even, and use it when we need it, dramatically change the equation? What's the state of batteries today, and what kind of power storage might we want in the future? Let's take a look.
We produce some 22 trillion kilowatt hours of electrical energy every year, much of which gets lost or dissipated through generation, transmission, and inefficiencies. If we could somehow recapture or store this wasted energy in batteries, it could dramatically slow down our rate of CO2 emission. But surprisingly, today's battery technology isn't that far removed from the acid batteries used in the American Civil War. Despite some advancements, our current batteries can't store and deliver power with the sustained punch, performance, and portability of other sources, like oil natural gas, and coal. But if they did, we could store electricity from variable sources like the sun and wind and other low-carbon sources, and then use that energy on demand. Battery limitations can be best illustrated by the current state of electric-powered vehicles, which can travel about 160 kilometers before they need a recharge. But to be comparable to today's gasoline and diesel-fueled vehicles, batteries would have to sustain a single charge for up to 800 kilometers. The development of these super batteries would allow us to harness a greater amount of clean energy, capturing it when it's cheap and abundant, and using it when and where required, possibly enabling us to power larger appliances in our homes and offices, or even large-scale industrial vehicles and equipment. A super battery that packs 5 to 7 times more punch than what we have today would be transformational. What will it take to produce such a battery by 2030?
Our thanks to the WGSI team and the production crews for putting those 4 videos together. Robin Batterham. Batteries were first invented around the time of the American Civil War and haven't advanced substantially since. Have we been stuck in a rut for 152 years?
Wilson, I'm not sure that we're stuck in a rut, but certainly you're seeing some of the same technologies, pretty similar to what's been around a long time. But this is very characteristic. One of the key things is not so much where is the next transformational technology, but there are things happening there in batteries, of course. It's how do we integrate things together? We're all so, let me give you one example. We're all so familiar with GPS. Nowadays, when you take a photo with your smartphone that has its GPS on, you've got to remember to turn it off so that when somebody gets that photo from you, they can't actually tell where you were at the time, but leave that as an aside. What my point is that GPS, while it was transformational, was not a scientific breakthrough. It was adding together several things into a package which became transformational. And that's where I see quite a bit of battery and storage in general heading. We've got to have a much more systems-type approach. This linking things together that we mightn't have otherwise. There's a lot that can happen, but it's going to require a different approach, a systems approach.
So would you say, though, that we're not at the point where we can match a tank of gasoline? That would be the nirvana, wouldn't it?
I think cars and gasoline and electric vehicles are sort of one way, but if we use the multi-prong approach, one of the first things that we might ask is, well, actually, do we want to run around in electric cars, or in a transition, do you want to run around in cars from initially run on natural gas and in time on biogas? That's just one aside to the sort of thinking that says, is it just about batteries? And the answer is, if you want to stay pure electric, then perhaps having your fuel that you're going to generate the electricity from on board and a fuel cell is a far more efficient way of going than having to crack the code on a battery which is 4 times the power density of existing ones. Not that I argue against trying to do that, but that's a pretty tough nut.
Yeah, that is a challenge. Physics and chemistry don't seem to be cooperating, do they? But storage, when it comes to the grid, we've been talking a lot about the grid and the legacy systems we have. Storage has been a little bit of the ugly duckling in that network, hasn't it, until relatively recently. Tell us about that.
Well, Wilson, you're right there. Storage has been an ugly duckling, and in some ways you go back to the stuck in the rut. Since Leyden with capacitance, and Faraday for that matter, who invented supercapacitors, but he just didn't have the technology to make the nano-sized particle that's needed to make a supercapacitor. But start putting those things together and you do get somewhere. So I make 2 points. Firstly, a combination of a very good battery and a very good capacitor gives you the best of both worlds, and it's still something which is very compact. And you're starting to see this, in fact, in some of the electric vehicle applications, where instead of having a battery which can give you a huge amount of power very quickly, which is what you need for accelerating, nobody likes having to have slots in the floorboards and you put your feet on the floor and pedal sort of thing. Instead of having that, you use capacitors to give you the acceleration part of it, and in fact batteries with much lower power draws on them because they can last a lot longer. The difference, it's like in humans between sprinters and long-distance runners. Use the capacitors for your sprinting and batteries for your long-distance running. But it keeps coming back to this thing of saying we don't have to have the scientific breakthrough, desirable and all as that is, stitching elements together. I give you one more. If you took all of the refrigerators in Canada, and they're turned over on about a 10-year plus cycle, whether they need be is another matter, and for each new refrigerator said, because we're getting smart grids all over the place, you are going to have a phase change material heat unit in it. And what can that unit do? It can allow that fridge to be turned off for 6 to 8 hours each day and yet still deliver the thermal load. So that fridge, all of a sudden, that freezer, all of a sudden now has 6 to 8 hours through the day where it doesn't need electricity. So the smart grid can start doing different things with it. These are the sort of examples on storage that are a little bit out of the box, or into the box in this case, a freezer box, that allow you to actually transform what we're doing now.
There you go, ladies and gentlemen. The revolution starts with your refrigerator. If we were able to bottle electricity, which is what we're talking about here, if we're able to bottle electricity and bleed it out during the week as we like it, that would have a dramatic impact on, you know, cities, buildings, factories. We just don't have that capacity at the moment, do we?
We don't have it at the moment, but part of that is because we haven't had to have it at the moment. What we're seeing now, and the purpose of this whole session here, and I invite everyone to have a think about it, is why aren't we moving faster? Fundamentally, why is it, especially when you see the videos that we've just gone through and hear from the sort of experts that we've got gathered here, why aren't we moving faster? And I'd suggest to you something very simple that I hope, it's non-scientific, although if you regard psychology as scientific, it's acceptable. It's standard Kubler-Ross theory that says, when you lose something, what happens? Well, if you get fired from your job, the first thing is you tend to deny it. If they can't fire me, I'm the expert in the area, or something like that. Then you get rather angry. How could they possibly do this? Don't they realize, etc., etc.? Then you resolve yourself to whatever it is, and you start thinking, well, actually, I'm pretty good at these things. I'll get on with it. Think what we're doing here today. Climate-wise, we haven't got angry about our forebears, the way they built the systems, the legacy that they've left us with, and the lack of options that it gives us for the future. We haven't got angry enough to turn around. We're still in denial mode, by the way, and I'm not talking about climate skeptics. We're just broadly in denial mode that we don't have to do much yet. So we've got to get angry about our forebears, and I'm not sure whether we're all a bunch, Your Excellency, a bunch of losers, but I like the Genesis argument there, and actually say to them, thanks folks, you left us some wonderful legacies and some terrible ones. And then we've got to get on with the resolve stage. And that's what I hope this session is very much about.
Well, Robin, we won't be firing you. You're definitely hired. Jatin.
I want to build on one or two points that Robin has been on to, and it is around the question of what I call integration of a complex system and the holistic view of things. Storage is actually not one solution, and it's a very complicated system. We've been looking for a perfect storage solution for the last 100 years and haven't found it yet. And the reason is that the there are multiplicity of applications and needs on the grid, and I don't want to make it too complicated, but concepts of spinning reserves and stability of the system, and so there are different needs on the system for what storage can provide. There is no one thing that matches it. That being the case, as you emerge into let's call it renewable forms of generation and greater integration of the electric vehicles into the grid, now you can begin to think in terms of the batteries in the cars providing de facto storage that we've been looking for over the last 100 years or so, and provide value to the system in ways that we have not envisaged so far. So I would like people to think of the Yorkdale shopping mall, solar charging stations. You go in there, do your shopping, out you come, and it's $1.10 charge for having parked there, and your car is charged up, and you've displaced all that molecules of gasoline. It's not all that far away, we're just about there, but it will require very powerful integration with both the distribution and the transmission system grid. So that notion is where we begin to think.
This is why it's been such a difficult problem for everyone, because it requires all this integration, doesn't it, Walt? You've got some points.
Well, I again come at this from a slightly different angle, because I have a problem with this notion that we have been taught in the last, particularly in the last 20 years, that electricity is a commodity and that what's important is buying and selling kilowatt hours. To me, electricity is a process. It's a process in technology, and it's a process in the whole technological system. So if you are concerned about how to make this a stable system and how to make this system function, doing all the different things you want it to do at different times and so on, you've got to think of it in terms of the dynamics of the system and the way the process actually functions, with all the different components that we have been hearing about. Because then you have to start thinking about who does what for whom on what basis. You then got to start thinking about how the decisions get made, how the finances happen, and you have a continual interaction between the science and technology, the system technical process, and the social process that makes the system function. And I think this week we're going to have to keep the social and political and economic aspects of this at least in the background of our minds, because they are ultimately going to be the determinants as to whether we can do this or not.
I guess ultimately, yes, we are looking at the science, but it has to make sense from a cost perspective, doesn't it, Barry? Because otherwise you'd build solar power satellites and transmit power to Earth, or, I don't know, reactors on the moon or something.
Exactly. There's many things we could be doing now, we might have done in the past if we could have afforded it, or if society had decided to invest in that. And as you said, we could have cities on the moon, we could be mining the asteroids and so on. Technologically, that's all feasible. But it's no good just saying that there's enough sunlight reaching the Earth every hour to power all of human civilization for a year. That's fine, but we've got to work out how to capture it, how to transport it, how to store it, and how that marries with alternative forms such as fossil fuels that we've used in the past and need to evolve away from, uranium, other forms of renewable energy and so on. It's a big challenge.
Well, ladies and gentlemen, we're coming to the end of this session. I think we've learned quite a lot about the scope of the problem, our present-day capabilities, and our needs for tomorrow. I'd like to thank our panelists, Barry Brook, Walt Patterson, Jatin Nathwani, and Robin Batterham for their insights. Now the real work begins. Our delegates will be collaborating over coming days with the aim to deliver the Equinox communique on Thursday. This will frame the most promising technologies and systems we'd suggest that we should pursue over the next 20 years, plus the implementation steps to begin realizing a more sustainable energy future. It won't be easy, as you can tell from the discussion tonight. It won't be simple, but we're approaching the problem from the perspective of science first, because we know it works and we know it has delivered the greatest benefits to humanity. Thursday's communique will be expanded upon in the coming months and become the Equinox Blueprint. This will be used as a roadmap to help guide research, development, and investment over the next 20 years and beyond. It's our hope that the blueprint will become a valuable tool for policymakers, business leaders, and citizens, allowing them to get on with the important work of realizing our energy future. I will see you tomorrow. Thank you.
Thank you very much, Wilson, for navigating our way through the issues and ideas that will be addressed more fully this week. Now, for those of you online, if you appreciated this introduction to the summit, then we invite you to tune back in for the daily plenary sessions, the public lectures, and the agenda with Steve Paikin on TVO. You can learn about all of the topics, all of the guests, and all of this programming by visiting tvo.org or wgsi.org.
Ladies and gentlemen, we are now coming to the end of the opening session. For those of you on site here in Waterloo, please join us for a reception just outside on the main level. And for those of you watching at home, we will be back online tomorrow morning at 9 a.m. with our inaugural plenary session, and that's Waterloo time. Would you all now please rise for the departure of His Excellency, the Right Honourable David Johnston, Governor-General of Canada. Mesdames et Messieurs, voulez-vous lever, s'il vous plaît, pour le départ de Son Excellence, le très honorable David Johnston, Gouverneur-Général du Canada.